On the initial reading of this question, it is clearly to do with velocity time graphs. This type of graph has certain key information of which we should be aware. Firstly, notice that as the acceleration is the rate of change of velocity, the acceleration is given by the gradient of the graph at all points. Also, it is important that we realise that on a velocity time graph, the distance travelled is represented by the area beneath the graph for any particular section of that graph. These areas may be found either by simple area calculations or integration should this be required. We will now move on and attempt to answer this examination question. Notice that during the first 3 seconds we have that the velocity is given by the formula 6t minus t squared. This is the curved section at the beginning of the graph, and we will use this to calculate the acceleration. Notice that the acceleration is given by the derivative of the velocity, and so we have that a must equal 6 minus 2t, and not forgetting that the units of acceleration are meters per second squared. Firstly, we need to appreciate that the distance travelled will be given by the area underneath the graph. This area will be obtained by integration. So we need to integrate the function for v between the limits t equals 0 and t equals 3. This integration will yield the following result. We can see that this gives the result of 18 meters as required. In this part of the question, we need to calculate the time required to run 100 meters. Now, from the previous part of the question, we already know that during the first 3 seconds, a distance of 18 meters is covered. We can add this to the graph. Having done this, we now need to find out how much longer it needs to run in order to cover the remaining part of the 100 meters. We can see from looking at the graph that we now need to run an additional 82 meters. If we assume that covering this 82 meters takes an additional t seconds, then we can proceed as follows. Now, the rectangular area representing this 82 meters has a width of t and has a height of 9 from the 9 meters per second. So this gives us that the 82 must be 9 times t, or t is 9 1/9 seconds. From this we can now see that the total time to cover the 100 meters is 3 plus 9 1/9, or 12 1/9 seconds. In this part of the question, we need to calculate the time required to run 200 meters. From previous parts of the question, we know that during the first 3 seconds a distance of 18 meters is covered. We will next proceed by calculating the distance covered between the times t equals 3 seconds and t equals 22 seconds. This is the area represented by the rectangle on the graph. Adding this information to the graph, we can see that the total distance covered in the first 22 seconds is 18 plus 171 meters, which is 189 meters. To have a total distance covered of 200 meters, we require an additional 11 meters to be the distance covered represented by the third section of the graph. The section of the graph beyond t equals 22 seconds represents constant acceleration, and so can be solved using the SUVAT equations. Notice that this work yields 2 potential solutions. However, it is the first value of t equals 1.28 seconds that we require. So the total time required to cover the 200 meters is 23.28 seconds as illustrated. In part 4 of the question, there was an additional time of 28.72 seconds which was rejected. The aim of this section is to show how if the graph were continued past 23 seconds, this solution would also become valid. Notice that the information from part 4 of the question has already been added to the graph. The additional yellow line also shows the continuation of the graph past this point. And should the motion continue past the point where the velocity is 0, then this is illustrated by the red line where the velocity becomes negative and s starts moving backwards, eventually returning to the 200 meter point in the time shown. So if the motion were continued past 22 seconds, then the graph after the 22 second point would look as follows. Notice the graph has been drawn to show time from 0. We will first calculate the time for the velocity to hit 0. Using v equals u plus at, we can see that this time is in fact 15 seconds. This time of 15 seconds has now been added to the graph. Notice that the area travelled during this 15-second time is given by the area of the triangle, which is 9 times 15 divided by 2, which is 67.5 metres that has been added to the graph. If we now consider the section of the graph where the velocity is negative, we can see that the time elapsed from 15 to 28.72 seconds is 13.72 seconds. And for this section of motion, we have the following values. Should we now calculate the distance travelled in this section using s equals ut plus half at squared, we can see that we get a distance travelled of 56.5 metres in the negative direction, and combining the two sections together, we have the 11 metres that was required in part 4 of the question. Thanks for listening. As we have previously used the SUVAT equations in this work, we will now consider their derivation. The graph illustrates an object which accelerates with constant acceleration a from an initial velocity of u to a final velocity of v over a time interval of t. Now the acceleration a is the change in velocity over the change in time, which is v minus u divided by t. Rearranging this gives us that at is equal to v minus u, and v is then equal to u plus at, which is the usual form of this first equation. If we now consider the distance travelled, the distance, which is denoted by s, is given by average velocity multiplied by time. And since we can calculate the average velocity simply by adding the initial and final velocities, we have that s is equal to v plus u all divided by 2, which gives the average velocity, multiplied by t, which represents our second useful equation. It is perhaps also worthy of note that this formula for s is in fact the formula for the area of the trapezium illustrated. We will now eliminate v from these equations by substituting v from equation 1 into equation 2. Equation 2 gives us that s is equal to u plus at, replacing the v, all divided by 2 and multiplied by t. This simplifies to s is equal to 2u plus at all divided by 2, and then this is in turn multiplied by t. Separating these terms, we get that s is 2ut all over 2 plus half at squared, which we usually write in the form s is equal to ut plus a half of at squared, which is our third important equation. In a similar way, we can now consider eliminating t from equations 1 and 2. From equation 1, we get that at is equal to v minus u, which in turn, on rearranging, gives us that t is equal to v minus u, all divided by a. If we then substitute the value of t into equation 2, we get s is equal to u plus v all over 2 multiplied by the value of t, which is v minus u all over a. This in turn simplifies to s equals v squared minus u squared all over 2a, noticing that the top is the difference of two squares. If we then multiply through this equation by 2a, we get that 2as is equal to v squared minus u squared, and then rearranging this equation into its more usual form, we get that v squared equals u squared plus 2as, which is the usual form for our fourth equation. I hope this has proved of some use to you, and once again, thanks for listening. Bye.